Okay, so in this video we're going to look at the three types of number systems that occur in a computer system. Right, so those would be binary, hexadecimal, and decimal numbers. Right, so decimal is the one that we use in our day-to-day type of experience. So it has 10 digits. Right, so the digits 0 to 9, right, and it's often called a base 10 number system. Okay, so the base is the number of digits. So binary numbers have only 2 digits, 0 and 1. Okay, so they are a base 2 number system. And then there is hexadecimal, right, which has 16 digits. So it has the regular 0 to 9, and then 10 to 15 is represented by the values A to F, capital A to F. Okay? And it is considered a base 16 number system. So what we really want to do is learn how to represent these numbers and what they really mean when we write a number down, and be able to convert back and forth between the different types of number systems. So let's take a look at an example first. So I'm going to look at the decimal number 2673, or 2673. So I'm going to write that like this, with a little subscript down there so you can tell the type of number system that I'm using. Right? And to understand this, we have to kind of go back to elementary school and think of our place values. Okay, so what this is showing us is that this column here, remember, that's the ones column, right? And this is the tens column, and this is the 100s column, and this is the 1000ths column. So to get the number 2673, you have 3 ones, 7 tens, 6 100s, and 2 1000s. Right? So if you were to write that out kind of in long form, you'd have 2 1000s, and you have 6 100s, and you have 7 tens, and you have 3 ones, right? So when you add it all up, you've got 2000 plus 600 plus 70 plus 3, and that gives you your 2673 as a number. Okay. Now these place column values are not just random, like why are they 1, 10s, 100s, thousands? Well, that is because of the base of the number system. Okay, so 1 is really 10 to the exponent 0. 10 is really 10 to the exponent 1. 100 is 10 to the exponent 2, and 1000 is 10 to the exponent 3. So the place values are really just the base of the number system to a different exponent based on what column that exists in it. Okay, so that's going to be important, because if we were to look at, say, then a binary number, okay, we wouldn't have the ones column, the tens column, the hundreds column, and the thousands columns. They would be different because we only have a base of 2 in our number system. So if we were to look at the the binary number, let's say 1 1 0 1 0 base 2, then this column here is the 2 to the 0 column, okay, the ones column as well. Okay. This column would be the 2 to the ones column, or the twos column. This one would be the 2 to the 2's column, or the 4's column. This one would be 2 to the 3, or the 8's column, and this one would be 2 to the 4, or the 16th's column. So the 1's, 2's, 4's, 8's, 16th's column. So this binary digit, if you were to try to represent it in decimal, we could do the same thing we just did. Okay, so there's 1 16's. There is 1 8's. Oops. There is no 4's. There is 1 2's, and there are no 1's. Okay. So if you add all of that up, you get 16 plus 8 plus 0 plus 2 plus 0, that is 26. Okay, base 10. So if you wanted to convert from binary to decimal, okay, you just have to know what column it is, and you can add everything up together. Now Converting to hexadecimal is the exact same process. So if you had a hexadecimal number, let's say 3 BD base 16, okay, then this column here is the 16th to the 0 column. This column is the 16th to the 1's column, and this column would be the 16th to the power 2 column. So you'd have the 1's, the 16's, and the 256ths column. So if you wanted to convert back to decimal, right, you would have 3 256's. Now B, that would be the equivalent to the number 11. Okay. So you'd have 11 16's, and you would have D would be 13. So 13 1's. Okay. So when you add all of that up, it would end up totaling 957 base 10. Okay, so there would be an expectation that you should be able to convert binary and hexadecimal numbers into their decimal equivalents using this method. So if we want to go the other way and convert decimal numbers into either binary or hexadecimal, it's just a matter of dividing by the base of the new number system, or continually dividing by the base of the new number system, and then looking at the remainders of that division, and that's going to give you your new number. So if I wanted to convert 97 in decimal to binary, okay, then I start with my number 97 and I continuously divide it by 2. So 97 divided by 2 is 48, but it has a remainder of 1. So you got to kind of go back to your division from elementary school to figure that out. And now I take 48 and I also divide it by 2. And that's 24, but I have a remainder of 0 this time. And then 24 divided by 2 is 12 with a remainder 0. And 12 divided by 2 is 6 with a remainder of 0. And 6 divided by 2 is 3 with a remainder of 0. And 3 divided by 2 is 1 with a remainder of 1. And now 1 divided by 2 is equal to 0 with a remainder of 1. Okay, and there's no point dividing 0 by 2 because you're always just going to keep getting 0 after that, so I can stop. So you can see over here, I've generated a binary number. So how do you read that? Because there's two options. You could read it downward, which is 1 0 0 0 0 1 1, or you read it upwards 1 1 0 0 0 0 1. Okay, and it turns out you read it up. Okay. So read up to get the answer. Okay, so your binary number works out to being 1 1 0 0 0 0 1. Okay, and you can kind of check that in your head as well, because based on what we did before, here's the ones column. Okay, so there's one of those. This is the 2s, 4s, 8s, 16s, 32, so there's a 32 and there's a 64. So 64 plus 32 plus 1 would give you your 97. Okay. If you did it the other way, then it wouldn't make sense. You wouldn't get the same number. So there's always a way to check that you're doing that correctly. Okay. And if you wanted to see another example of that, then let's maybe try 44. To binary. Okay, so 44 divided by 2 is 0. Okay, oh sorry, not 0. 22, remainder 0. Okay, 22 divided by 2 is 11, remainder 0. 11 divided by 2 is 5, remainder 1. And 5 divided by 2 is 2, remainder 1. And 2 divided by 2 is 1, remainder 0. And then 1 divided by 2 is 0, remainder 1. Okay, so read up, and your binary number would be 1 0 1 1 0 0. Okay, convert to from decimal to hexadecimal. Instead of dividing by 2, I'm going to divide by 16. So if we wanted to convert, let's say 943 base 10 to hex. Okay, I would take 943, divide by 16, because that's the base of the number system. That gives me 58, right, with a remainder of 15. So how do I know that? Well, so if you take 943 and divide by 16, you get 58 point something show up on your calculator. Okay, so 16 times 58 is 928. Okay, so 943 minus the 928 gives you the remainder of 15. Okay, so now I do 58 divided by 16, which is 3 with a remainder of 10. So the same process. 58 divided by 16 is 3 point something on your calculator. 16 times 3 gives you 48. So 58 minus that 48 gives you the remainder of 10. And now 3 divided by 16 is equal to 0 with a remainder of 3. Okay. So now you might look here, well, these are not hexadecimal digits, but if we write them as what they should be, right? So remember that 10 is really A, and 15 is really F. 3 is still 3, and you read up, then the hexadecimal number is 3AF. base 16. Okay. And maybe one more. Let's maybe try, I don't know, maybe 352 base 10 to hexadecimal. Okay, so 352 divided by 16 is exactly equal to 22, so it has a remainder of 0. 22 divided by 16 is equal to 1 with a remainder of 6. Okay, 1 times 16 is 16, 22 minus that 16 is 6. And then 1 divided by 16 is 0 with remainder of 1. Okay, so those are all in their equivalents, so I don't need to change it into the letters. So this would be 160 base 16. Okay, now you might be able to see why it's important that we write the subscripts here, because how would I know that 160 is in hexadecimal and it's not just the plain old number 160? Okay, so when you're working with different number systems, sometimes it's beneficial for you to actually write the base, okay, to go along with your number system. So the last thing we have to do is learn to be able to convert between binary and hexadecimal, right? So there's a couple ways you can do this. There's kind of the long way, which is if you want to convert from binary to hexadecimal, you could go binary to decimal, then decimal to hexadecimal, okay? Or the other way around, hexadecimal to decimal, decimal to binary, because you already learned how to do that. But there is a not so much a trick, but perhaps a better way to deal with that. And you may have heard of, when dealing with computer systems, like bits and bytes. Okay, so a single digit in the binary system is called a bit, and 8 bits is called a byte. But what is nice about binary and hexadecimal numbers is that you can represent all 16 digits in the hex system with a 4-bit binary number. We call that a nibble. Okay. So for example, if you wanted the number 0, let's do it. Okay. Then that would be the equivalent of 4 zeros. So this is the nibble equivalent in binary. If you want the number 1, that would be 0, 0, 0, 1. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. And 8 is 1, 0, 0, 0. 9 is 1, 0, 0, 1. If you're clever, you can see how we count in binary, because just like we count in decimal numbers, we use up all the digits in the column before we go to the next column, okay? And then the first column gets reset back to 0 when it starts to count. So you can see that pattern show up when we start to count here. But then if you kept going, these are probably something that you could easily remember. And then if you're going to do a lot of computer systems, it would probably be smart to start remembering these values. So A is 1, 0, 1, 0. Then we get 1, 0, 1, 1. And then we get 1, 1, 0, 0. 1, 1, 0, 1. E would be 1, 1, 1, 0, and then finally F is all 4 ones. Okay. So why does this benefit us? It's because if you can write your binary number in nibbles, then you can just read off the hex value to it. So if you wanted to say convert, let's say the binary number is 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1. Okay, so if they're written as nibbles like this, then 0, 1, 1, 0, that's a 6. 1, 0, 1, 1 is B, and 1, 1, 0, 1 is D. Okay, so this is just equal to 6BD in base 16. Okay, right, and it would work out even if you didn't have like a full nibble here as well, because if you actually start over here and do 4 digits this way, 4 digits this way, and then whatever is remaining over, fill in zeros to make it 4 bits this way, you can still do it. Okay, so if you can write them in nibbles, you can just read off the hex values. Okay, and it works the other way as well. So if you convert, let's say A7 F4, oops, F4 base 16, right, to binary. Okay, so A is just going to be 1, 1, 0, 1, 0. 7 is 0, 1, 1, 1. F is 1, 1, 1, 1. And 4 is 0, 1, 0, 0. Okay, so there is your binary number in just translated into its equivalent nibbles. Okay, so it's actually really easy this way, much better than trying to say take this number here, going to decimal first, and then going from decimal to binary, right? This takes 3 seconds if you can remember what these nibbles represent in their hex equivalents.